Log on, tune in, find out. Another good idea from Cambridge.
I'm going to speak about some generalization of Littlewood-Richardson coefficients, as the title suggests. Well, let me say just a couple of words about the background and motivations of this work. In fact, about 10 years ago, in our work with Bruce Sagan, we found yet another way of calculating the Littlewood-Richardson coefficients. And the idea was that we take these coefficients and include them in a bigger family of polynomials, of homogeneous polynomials in a certain set of variables. So we can have polynomials of degree 0, which turn out to be exactly the Littlewood-Richardson coefficients, that polynomials degree 1, 2, and so on. And the important thing is that all these polynomials can be calculated by using a recurrence relation. So polynomials of degree k can be calculated by using polynomials of degree k plus 1. So, and the top degree polynomial can be, well, explicitly known. And so using this recurrence relation, you calculate all these polynomials inductively and also the Littlewood-Richardson coefficients themselves. Well, but a bit 2 years later, in 2001, Graham proved a theorem about equivariant cohomology of the Flock variety, which implied in particular that our polynomials have to be positive in some precise sense. And our rule with Sagan was not positive, did not produce explicitly that positivity property. So in 2003, Knudsen and Tao gave another rule for the calculation of those polynomials. And they used the same inductive approach. And their rule was manifestly positive. So it's so-called puzzle rule. Well, and the last motivation for me was it's actually where the lectures of Eilenberg lectures of Bill Fulton about equivariant cohomology, when he emphasizes the cohomologies of the Grassmannian and Flock variety. So this prompted me to think of a way of modifying our original work with Sagan to get positive version of our rule. And in fact, that's what I'm going to tell you. But what's more interesting, that new rule actually produced a stability property. It's made explicit a stability property, which actually was not obvious from Knudsen-Tao rule, and actually they didn't know about it as Terry told me. Anyway, so let me start with. So my main theme will be combinatorial. I only use some applications, only mention some connections with other areas. Mainly, I hope to discuss applications to quantum immanence, how they can be multiplied by using this rule, and also applications to the equivariant cohomology of the Grassmannian. So to fix the notation, let's take usual English notation for diagrams. So as opposed to French or Russian, so this is how we depict diagram 553. So I also use two parameters of such diagrams: the weight and the length. So weight is just the number of boxes, and the length is number of rows in such a diagram. So let me start with recalling what the Littlewood-Richardson coefficients are, and where you could see them. So first point of reference is the representation theory of GLN. So take lambda. Think of lambda as the highest weight of GLN representation. So lambda has length at most n. Well, if it's smaller than n, we add zeros if required. So then tensor product of two such representations, v lambda and v mu, so will be, this is a finite dimensional representation. So while complete reducibility, we have direct sum of irreducibles. So the coefficients are the multiplicities are precisely the Littlewood-Richardson coefficients. So another place, if you work with the symmetric group, so an equivalent definition, essentially, you use inductive product of two irreducible characters. So take two symmetric groups, say SKSL. So chi lambda, chi mu are corresponding irreducible characters of these two groups, and you embed direct product into bigger group, SK plus 1, and induce direct product to this bigger symmetric group. Then again, this is a character, and as a character, this must be a non-negative linear combination of irreducible characters. And again, you see exactly the same coefficients here. Well, and a different context is the cohomology of Grassmannian. So let's take capital N as our space, Cn, and consider lowercase n dimensional subspaces there. So therefore, we have the Grassmannian, corresponding Grassmannian, and its cohomology ring has a basis of the Schubert classes, which are parameterized by all diagrams which fit a rectangle, namely n by m rectangle. So when m is difference, n capital and small m. So in particular, you have as a Z module, you have a basis of n capital choose n elements there. And surprisingly, the Schubert classes are multiplied by the same rule as in the previous two cases. So you have the same structure coefficients for the product of the Schubert classes. Okay, well, in fact, it may look surprising, but if you think of the reasons why the Littlewood-Richardson coefficients appear in all this context, so all of them are reduced to the product of Schur functions. So let me remind you what these are. So we'll work with an infinite set of variables, and given any partition lambda or diagram, I don't distinguish between partition and diagram, we first define the monomial symmetric function. So by definition, this is an infinite series which is obtained by symmetrizing a given monomial. Let's take a monomial degree lambda, so x1 to lambda 1, x2 to lambda 2, and so on, xn to the lambda n, and then use all permutations. I mean, not just permutation of these symbols, but all permutations of positive integers which give different monomials. So it gives you a formal series, but those formal series can be multiplied. So it's usual multiplication of monomials is extended to series. It makes sense. It's well defined. So it gives you a ring or an algebra if you consider this over a field, say over Q. You got the algebra of symmetric functions. So certainly there are some well-known examples. Let me just give you the formulas to fix the notation. So we got the power sum symmetric functions, sum of all powers, elementary symmetric functions, or complete symmetric functions. All of them are expressed as a finite linear combinations of the monomial symmetric functions. Of course, these are well-known formulas. Okay, so most important class is the class of Schur functions, which I will need. And here is the combinatorial definition of them. What we do, and I here use notation which is slightly unconventional. Instead of usual semi-standard tables, which you might be familiar with, I use reverse tableaus. So by reverse lambda tableau T, we mean filling of the boxes of our diagram with all positive integers, but in such a way that rows are weakly decreasing and columns are strictly decreasing. So we just reverse the ordering as compared to the semi-standard tableaus. So, and some notations, so usual notations, so the boxes of the diagram are labeled by a pair of coordinates, like in matrix notation. Ij is the row and column numbers. So Tij or T of alpha is the entry in that box. So this is an example of a reverse lambda tableau. Okay. So now here is definition of the Schur function. What we do, we'll take sum with respect to all possible reverse tableaus, and for each of them, write product of all variables corresponding to the indices which occur in that tableau. So it's basically the the same definition, the only difference we take different order. So here is a quick example. If you take just 2, 1, then you can put IGK there. Here is your Schur function here. And in particular, we can see that the elementary and symmetric functions are particular cases of the Schur functions corresponding to one row or one column diagrams, obviously. Okay, so well, it's easy to see that from this definition that the Schur functions are finite linear combination of the monomial symmetric functions, and this transition matrix is invertible, actually unitriangular. So therefore, the Schur functions form a basis, and you define the Littlewood-Richardson coefficients. Actually, that's the definition I'm going to use as the structure constants for the product of Schur functions. Okay, and some history for you. The first rule for calculating those coefficients was given in a paper by Littlewood and Richardson in 1934. But in fact, they only proved that rule for a particular case where one over the diagram has at most 2 rows. And so nevertheless, they called the result a theorem. So this was a theorem in their paper, but proof was only given for that particular case. So then Robinson published the proof of that rule later. But now it's actually, the language of that paper is very difficult to read. And the paper is difficult to read. And in fact, now it's recognized that there are gaps in his arguments. In fact, complete proofs were appeared much later. So maybe about 40 years after it was first formulated, it was proved by Thomas and Schutzenberger independently. And by that time, some combinatorial technique were developed, like Robinson-Shusted-Knut correspondence was introduced, and so-called Schutzenberger-Jeu de taquin, so certain sliding algorithm. So that was needed for those proofs. And now there are lots of versions of this rule involving various combinatorial objects, starting from trees, hives, honeycombs, tables, puzzles, and many other things. So I will only mention a couple of them. Both of them are related to that inductive procedure which I mentioned in the beginning. So let me remind you what the Knudsen-Tao-Woodward puzzles are. So in this context, we want to place the 3 diagrams which we're working with in a big rectangle. We can always choose sufficiently big rectangle to place all 3 diagrams and write each diagram or partition in a binary code. So what do I mean? I'll explain it by using an example. So if you take this diagram and put in this 4x7 rectangle, we just travel from the upper right corner to the lower left corner along the boundary of this diagram. Each time you go left, you write 0. You go down, you write 1. That's your binary code. So you go 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1. That's your binary code. And of course, there is one-to-one correspondence between diagrams and binary codes of length n plus n containing exactly n ones. So next, you write these 3 sequences, which you get by this procedure, along the borders of equilateral triangle. So you write lambda, well, I mean binary code of lambda here, then mu, and nu is the base of your equilateral triangle. And here is the theorem proved by Knudsen, Tao, and Woodward, so that the Littlewood-Richardson coefficient C lambda mu nu is equal to the number of triangular puzzles, which you can obtain by filling this big triangle with certain unit puzzle pieces. What are they? So here are the puzzle pieces. You have actually 7 of them, but in fact geometrically there are just 3. You have 3 zero triangles, but they can be used in 2 different orientations, or you can use 2 one triangles and actually 3 rhombi. But in fact this is 1 rhombi, but you can use 3 positions, 3 orientations of this rhombi. Okay, so now what does it mean to make a puzzle? Obviously, if you have 2 puzzle pieces, you can match them together if the boundaries agree. So you can add 0 with 0, 1 with 1. That's how you make puzzles. Okay, and let me illustrate it by an example. So let's calculate this coefficient using the rule. You have 2, 1, 2. We have these 3 diagrams and write them in binary code. So we choose smallest possible NNM. So this is a square in this example. So this is lambda, this is mu, this is nu. And here is your big triangle. So you need to fill this by those unit puzzles. So in fact, if you, let me briefly remind you what they are. So if you look at this possible puzzle pieces you can use, certainly there is only one rhombus can be used to fill the top of this. So you can only put this rhombus there. There is no other choices. Then you can see there are 2 zeros to 1s. You can only fill this by triangles. And then you follow down and by certain obvious considerations, you have a unique puzzle which gives you the number. So the Littlewood-Richardson coefficient is equal to 1. So, well, looking at this rule, you might wonder, is that really you really need to work so hard to calculate this simple coefficient? Of course, this is one which is given by the Peary rule, and we already knew this is 1. But the point is not in this. The point is that the Knudsen and Tau, and they actually use a similar or equivalent formulation to prove the saturation conjecture, some property of Littlewood-Richardson numbers, which I probably not going to discuss, but just to mention. So this point is not in effectiveness, but on the other properties of that rule. Now the second rule is the Tableau version, and it looks like this. So now we introduce some more combinatorial objects. We will work with sequences of diagrams. So each time you go from one diagram to other by adding one box whenever this is possible. So you add several boxes. You can go from one diagram to another. So for instance, what we need, we'll record this by writing the row numbers of those boxes which were added in each step. So we'll call this Yamanouchi symbol of such a sequence. So here is an example. If you take, say, such sequence of diagrams with snowflakes indicating where you added extra box, here is your Yamanouchi symbol, 2, 3, 2, 1, because you add boxes in row 2, 3, 2, and 1. This is how the Yamanouchi symbol is found. All right. Now, one more thing is needed. Now we need to agree how to read tableaus. We want to read them in a certain particular way by columns from left to right and from bottom to top. This should correspond to a reverse Chinese reading, I believe. So if you have such a tableau, so you read it starting from leftmost column and going upwards. So you read 2, 4, 5, 1, 3, 5, 1, 2, 4, and so on. So it gives you the column word. So what something we read, this is called the column word of the corresponding tableau. And in fact, this also defines column order for the boxes of any particular diagram. So we just read them in that particular order. So, all right, and finally, one more thing which is needed. Now, for each two diagrams, we want a condition for a lambda tableau. We need to say what this means for it to be nu bounded. So this means just the following. If you take a tableau, then all the elements in the top row should be bounded by the column length of the diagram of nu. So I will give you an example to explain what this means. So in fact, such tableaus only exist if lambda is contained in nu, and here is an example. So this is our lambda, and mu is a bigger diagram. So you just count column lengths of this in this diagram, and here is these are the restrictions. So we have 5 columns, 5 boxes in the first column. So maximum entry you can put there is 5. So 5, 5, 4, 4, 2 is that. These are the maxima of the entries you can put in the first row. So this certainly restricts the number of possible new bounded tableaus. In fact, there is only a finite number of them, because remember, our columns are strictly decreasing. So this gives you a finite set of tables. And why that condition is actually holds, imagine if you had new going like this. So we could only put one in this box, but we wouldn't be able to fill the second box because of strict decreasing condition. Okay, and here is the theorem. So this is a one of many interpretations of the Littlewood-Richardson rule. It says that the Littlewood-Richardson coefficient equals the number of common elements in the two finite sets. So one set is obtained by using the pair of diagrams lambda and nu. You list all possible column words of all new bounded reverse lambda tableaus. So it gives you a certain finite set of words. And second, you take all Yamanouchi symbols of all sequences from mu to nu. And now see how many common elements you have. This is your Littlewood-Richardson coefficient. So this is how this works. And in fact, that theorem is a particular case of a more general result, which I'll come a bit later. And in fact, it is also possible to prove that theorem directly by establishing an bijection with the puzzles of Knudsen and Tao, and this was given by Tao. So let me illustrate by an example how you use that rule. So if you take a lambda mu and nu to be to 1, nu is 3 to 1. So these are all new bounded lambda tableaus. They all are listed here. There are 6 of them, and these are all column words. So now you need to look at which of these column words can be Yamanouchi symbols of the sequences from mu to nu. Well, in fact, you can list all the sequences. So there are exactly 6 of them. It's easy to see because you can add one box and every row 1, row 2, row 3 without any restrictions. So there are 6 permutations on 1, 2, 3, and you can see how many common elements you have. How many? So did you notice? So if you need to come back, so you see that there are exactly 2 elements here, which are permutations of 1, 2, 3. So the conclusion is the coefficient is equal to 2. So this is how this rule works. So of course, in practice, you may start with one of these finite sets and see how many elements of the set belong to the other set, as we did here. All right, now about this generalization. What we can do, and I explain the basic idea behind that. So we now want to view symmetric functions from a slightly different angle. Let's think of a symmetric function as a sequence now. So a sequence of symmetric polynomials in increasing number of variables. So like if you take this formal series as we had before, you think of this as an infinite sequence of symmetric polynomials, and all of them should be related or should be compatible with the evaluation homomorphism. You can get previous polynomial by putting the last variable to 0. So that's an equivalent definition, in fact, of symmetric functions. And the key idea is this: why do we use 0 here? Can we replace 0 by something else? Can we evaluate the last variable and a different point, not necessarily 0? And in fact, you can choose arbitrary sequence. So let's just pick a sequence of parameters, and that's what we're going to do. Let A, it's convenient to use to label them by all integers rather than positive integers. So this will be just sequence of variables, and we consider symmetric polynomials in n variables with coefficients in Q of A. So Q of A means just polynomials in this infinite set of variables. So here is the definition. You just take this evaluation homomorphisms and think of new ring as to be formed by all such sequences of compatible polynomials. So, or in other words, you can say we just take the inverse limit of this sequence of homomorphisms. and with obvious multiplication. So this defines what is called the double symmetric functions. That's a definition of that. And here is some examples. So if you start with these polynomials, sum from well, actually this is an analog of power sum symmetric polynomial, but we use these shifts in A. So if you evaluate xn with an, you certainly get the previous one. So this defines a double power sum symmetric function, so which can also be written as a formal series, as it's shown over here. And similarly, so in fact you can prove that this new ring is in fact the ring of polynomials in these variables. So these polynomials are algebraically independent over Q of A, and so you get all polynomials in this way. Well, obvious remark is that if you specialize all AI's to 0, you come back to the original ring of symmetric functions. So we can always check our formulas and by going to the classical case. All right, so it would not be that interesting if we wouldn't have analogs of Schur functions or Schur polynomials. Yes, actually these are Schur functions here, and by definition this is sum with respect of all reverse lambda tableaus as we had before. That's why I needed the reverse lambda tableaus here. So the only difference here, we take xt of alpha minus at of alpha minus c of alpha. So what is this new thing? C of alpha is the content of the box alpha, which is ij, just the coordinates. So this is j minus I, this usual combinatorial entity here. So, well, you need to check two things. First of all, this is if you restrict a set of variables to a finite set from 1 to n, you got a symmetric polynomial. This is already less obvious than for the classical Schur function, but it's still true. And then we need to check that they are consistent with respect to those evaluation homomorphisms. So here is an example that is how double Schur function looks like for this particular case. Notice these differences, j minus 1, k plus 1, this came from this content. And so in this example, you can see why the Schur function is consistent with those homomorphisms. So think, let's suppose that I, j, k only run from 1 to capital N. So we take a finite set of variables. So if n capital occurs in this tableau, then the n should be in this corner because of our conditions. So we have weakly decreasing rows and strictly decreasing. If n is there, it has no other place than to be in this corner. And the same holds for any diagram. So in that corner you should have n. But if you look at the formula and you specialize xn to n, you have the first factor xi minus ai. It will vanish. So therefore, those n's which occur in your tableau give zero contribution when you specialize. So therefore, you got from one Schur function to another. So they are indeed consistent with those homomorphisms. Well, now you can also define analogs of elementary and complete symmetric functions in the same way, just by taking symmetric functions corresponding to row and column diagrams, and these are explicit formulas. Even for them, checking that these are symmetric polynomials in X is still quite an exercise. It's not quite obvious, I would say. I forgot to mention actually where they come. They first speaking of the Schur functions. I mean, general formula like this. So these functions were first introduced in mathematical physics literature by Biedenhahn and Luke in 1991, 1992. And after that, MacDonald and independently Goulden and Green. I forgot to mention that actually Biedenhahn and Luke use a particular sequence of parameters A. So all the AI's were equal to I or minus I, something like that. So and MacDonald and Goulden Green introduced such functions for arbitrary sequence A. And in fact, already in the second edition of the MacDonald's book on symmetric functions, they're already there. He proved lots of analogs of the classical Jacobi-Trudi, Jambelian various other formulas which all hold for this class of functions. Okay, so now here is well, a definition which can be well, probably is one of the results. In fact, so you can define now these polynomials C lambda mu nu A as the structure coefficient in of this algebra of double symmetric function in the basis of Schur functions, of double Schur functions. So the double Schur functions form a basis. So if you multiply two of them, it should be a linear combination. But remember, we work over the ring of polynomials. So these are now polynomials in A. And in fact, they only depend on three diagrams. So I should mention that these coefficients were in our work, say, with Sagan, which I mentioned in the beginning. Those polynomials, or similarly defined polynomials, also depended on the number of variables. So you also had to work with a finite set of variables. So by using these reverse tables, you get rid of this problem, and you have these polynomials which only depend on three diagrams and not depending on any other variables. So what are the properties? First of all, by the degree argument, so you may notice that these Schur functions are homogeneous if we combined set of variables x and a. So this gives you the property they only non-zero where nu is smaller, weight of nu is smaller than the sum of lambda and mu. Now this is a homogeneous polynomial of that degree, sums of weights of lambda and mu minus weight of nu, a homogeneous polynomial in the a's. In particular case where this degree is equal to 0, you get polynomials of degree 0, and these are exactly the Littlewood-Richardson coefficients, which is also clear if you put a equals 0 in this formula. Okay, what else you can notice more or less immediately? They are symmetric if you swap lambda and mu. And there is another property which is a bit less obvious but can also be checked, that those polynomials only non-zero where both lambda and mu are contained in nu. So it gives you some kind of general idea how this polynomial look like. Okay, so the next question is how can we calculate them in a certain explicit way, and how would you do that? I'll give you the results. So this is what we need to use is slightly more general objects as compared to what I used before. We want to use so-called barred reverse lambda tableaus now. What does this mean? So imagine we'll take just a reverse lambda tableau, and we are given a certain sequence R from mu to nu with Yamanouchi symbol R1, R2, RL. So the condition is when you read your tableau by columns, as we agreed to read our tableaus, you should meet those numbers at certain places. Not necessarily one by one, but first you meet R1 somewhere, you keep reading, you meet R2, and so on. So if such sequence exists there, then this is an element of our set, and we just label those particular entries by barring them. So that an element of this set, tau lambda r, is in fact a pair. So it's consisting of a reverse tableau and a sequence of those entries which we mark by bars. So here is an example. So if we take the same sequence as before, 2, 3, 2, 1, and this is an example of such a, this is the barred lambda tableau, because when you read by columns, you can see that 2 here, 2, 3, 2, 1. So these numbers occur in that particular column order. In fact, with given lambda tableau, you can choose different sequence of barred entries. For instance, you can put bar instead here, you can put it there. So there are several possibilities to put barring for a given lambda tableau. Okay, so what's next? Now we also need to label our, I probably use the picture to explain what this labeling or marking means. So suppose that we have a sequence of diagrams as before, each time adding one box, and we take our barred tableau. So this is R1 bar, R2 bar, RL bar, our chosen entries which we barred. So what we want to do we want to mark all other boxes, not barred, unbarred boxes before R1 bar in the column order by row 0, actually by mu. So you can explain it like this. Let's just read our tableau as we did before. So as soon as you don't meet any but entry, you just put row 1 there. As soon as you skip it, then you put row 1. So all boxes in this region between R1 and R2 but labeled by row 1, then by row 2, and so on. So each unbarred entry now also takes a label or mark if you like. Okay, and here is the main result. So this is the theorem which I wanted to tell you about. We proved it independently with Victor Kramer in about 2007. In fact, I think our papers were not published yet. They accepted, but so 7 actually means where preprints appeared. So, but maybe it's this year when the paper will be published. So the rule is this: what you need to do in order to calculate this polynomial is to take the sum with respect to all sequences from mu to nu, as we did before. Now, for each such sequence, you then take this barred lambda tableaus T, and we also need to assume that all these tableaus are nu bounded. So we take all nu bounded reverse lambda tableaus which have those barred entries somewhere in between. And for all unbarred entries, you write this particular product here. So what is here? So T of alpha is just the entry in that particular box. Rho of alpha is that label which we introduced, and rho of alpha, T of alpha is that T of alpha's component of that diagram, and these things were, in fact, C of alpha is the same C of alpha content as before. In fact, we proved it by different ways. Kramer used Stambridge approach to the, well, Stambridge, a few years ago, Stambridge gave what is called concise proof of the Littlewood-Richardson rule, which is quite short one, and using some involution on tableaus, and Kramer used that idea. So in my approach, I used the same idea as we used with Sagan by using this induction. I'll explain it in a second. So one other part of the theorem is that in each of these factors, we'll automatically have this property. Then rho of alpha, T of alpha is greater than C of alpha. So if you look at this formula, what does this mean? The index of this variable is always smaller than index of these variables. So this is, in fact, reflects that positivity property, which I mentioned, say a few words in a moment. But first, what I have here, if we take that particular case where the weight of nu is equal to the weight of lambda plus the weight of mu, let's see what we have. The number of elements in the sequence R from mu to nu is exactly the same as the number of elements in our tableau. So all our entries should be barred. Bars are everywhere. So there is no single unbarred entry, so the product is empty. So that product is actually equal to 1, and therefore the sum is just count the number of Yamanouchi symbols or column words, if you prefer, which are compatible. So that's where that theorem which I formulated earlier came from. So it's, you take intersection of these two finite sets, and that's exactly the particular case of this theorem. And the second property which I mentioned is that this polynomial is Graham positive. So that's the positivity property. So this is a polynomial in the differences ai minus aj for all I less than j. So as I said earlier, Graham proved that is more general context of the equivariant cohomology of the Flack variety. So this is, you may recognize positive roots here. So that's where this association come from. So anyway, so this is manifestly positive. Not manifestly, I should say, but explicitly positive by the second property here. So, and an illustration as before, so let's calculate this polynomial, see how this works. So lambda 2, 1, mu is 3, 1, mu is 4, 1, 1. So remember, all our tableaus should be new bounded. So therefore the maximal entries here 3 and 1, and we have just 3 possible new bounded tableaus. Now we have just 2 sequences from mu to nu. We can add 2 boxes in row 1 and row 3. So 1, 3 and 3, 1. And now what's next? Now let's take the first sequence 1, 3. We should read, while reading our tableau, we should meet 1 and 3 in that particular order. First 1, then 3. You can see there is only one possibility to do that for this tableau. And this gives you contribution. So this is 1, 3 abar entries. There is only one unbarred entry here. And so these are the parameters. T of alpha is 1, row of alpha is labeling here is 4, 1, 1. So you'll get this contribution, a minus 3 minus a 0. And similarly, for there are 2 other bar tableaus which gives these corresponding contributions, and this is the answer. So that's this is first degree Littlewood-Richardson polynomial and how it looks like. So now another example when you can see the whole picture. You just multiply 2 Schur functions, 2 double Schur functions, you can see how all the coefficients look like. In fact, if you look at the top row here, this is the classical part. This is in fact the Peary rule. Well, all coefficients are constants, they're just all equal to 1 here. And then the other coefficients here are particular Littlewood-Richardson polynomials for other degrees. Well, yet another example. There is a very particular case. Well, all 3 diagrams are the same. Took lambda, lambda, lambda. Then you'll get rather interesting polynomial here, which factorizes, and just the product of all of such factors here. You can call it a split hook polynomial. In fact, if you replace all i's by minus I that's originally introduced, then you'll see exactly the product of the hooks of your diagram. Okay, so now a few words about the proof and the argument which was used there. We'll calculate that polynomial by induction on the difference nu and mu, or otherwise so the length of the sequence R from mu to nu, which is the same. So induction induction base rather is based on the vanishing theorem of Okounkov, which he proved in 1996, and it says the following: even though our double Schur function is a formal series, you can make a substitution there. You can substitute variable for x. Why you can do this? You can, in fact, you can substitute a row. This is sequence a1 minus row 1, 2 minus row 2, and so on. So if you take particular diagram row, then eventually all the elements here will be nth element will be equal an. And remember the homomorphism. We evaluate xn at an, which gives you the previous one. So therefore, this says that actually this evaluation is well defined. And in fact, you'll get 0 where unless lambda is contained in rho. If lambda is equal to rho, so if you weigh as lambda, you got non-zero. In fact, I didn't write it, but you'll get exactly this polynomial here. So that polynomial is exactly the value of the double Schur function that particular sequence. So using that, you can get the first induction base. So C lambda mu mu, that is your sequence is just one single diagram. You don't go anywhere. And here is the answer. You got just the value of the Schur function at that particular point. So this gives you the combinatorial formula by definition of the double Schur functions. So that's the expression, and it agrees with the theorem. So next step is to use this recurrence. So that's the key point, actually. That's the recurrence relation, which allows you to calculate polynomials of degree k in terms of degree k plus 1. So what is here? A mu minus a nu, this is actually the a polynomial in the denominator. So sum of differences of this ith values of a nu and mu. And here summation is taken with respect to those diagrams mu prime, which can be obtained from mu by adding one box. So altogether, this is in fact gives you smaller degree, and similarly nu minus is obtained from mu by removing one box. So altogether, this gives a recurrence relation, and starting with the top one, so that top one is given, you now calculate all that. What is the problem here? The problem here is that that looks like a rational function. We know beforehand this is a polynomial. This should be divisible by this denominator. But how to divide it? So it's rather non-trivial denominator, the sum of differences of several terms. So the problem is actually to find a combinatorial way to get polynomials in each step. All right, so now returning to the puzzles. In fact, there is also a version of the puzzle rule, the one I mentioned in the beginning, for these polynomials. So remember, just to remind you what you need to do, you have three diagrams lambda mu. As before, you write corresponding binary codes along the sides of this equilateral triangle, and then you again play the same puzzle game. The only difference here, and that's the theorem of Knudsen and Tao 2003, that this polynomial is in fact reformulation. They didn't use the same definition, but in fact it's equivalent. So it equals to the sum of weights of triangular puzzles which you can make, but using an additional puzzle piece. What is this additional puzzle piece? Is this one. So this is rhombus, exactly one, and exactly in this particular orientation you can use it. So remember, the previous usual rhombus was labeled by 1001. Here we use opposite labeling, and you can use all previous puzzles as well. So what happens if you now make this puzzle and that particular puzzle occurs somewhere, then you write its coordinates like I and j, like indicated, and for each such a puzzle you write corresponding product, ai minus m, j minus m. Remember, m was the other side of this rectangle. So we had rectangle n times m. And well, if you have several of them in that rectangle, just write the product of such differences. If you take sum with respect to all puzzles, you got the same answer. And their proof uses the same approach. So they started with the biggest one. So they showed how this biggest polynomial can be written in terms of puzzles, and then interpret this recurrence relation in terms of puzzles. What happens to the puzzles when you divide that expression by the denominator? All right, so now a couple of applications of this rule of our theorem. Using that theorem, you can calculate the structure constants for the basis of the center of the universal enveloping algebra for GLN. And here how this works. So we need to use that basis called, which consists of quantum immanence, as was constructed by Okounkov in 1996. So let me explain what this is. Let's start with diagram lambda, which has at most n rows, and it has exactly k boxes. Then we consider the irreducible representation V lambda corresponding to lambda of the symmetric group Sk, which is labeled by that particular diagram with k boxes. So then that we can representation space admits the Young basis, and we'll take the orthonormal Young basis in that space, which I call VU, and it is labeled by all standard lambda tableaus. So standard means that we take all k numbers from 1 to k, put them bijectively in the boxes such that they increase along rows and increase down the columns this time. So this is now usual standard tableaus. And then next step, we introduce this matrix element. For particular fixed tableau, we introduce phi u. This is an element of the group algebra for the symmetric group, which is just calculated by using the action of all elements of the symmetric group on this basis. So we act then take inner product with VU and multiply by S inverse. So that's an element of the group algebra. Next, we consider the natural action of the symmetry group on the tensor product of k copies of Cn. That's something, picture which you use in the classical Schur-Weil duality. We just have this k copies of Cn. And what we need this for, we can think now of this element as acting in that space, and therefore choosing basis in Cn, we actually choose canonical basis. We can think of Phi as an element of tensor product of k matrix algebras. So we just want to think of this element as an element. Well, actually, this is phi capital U. It is the image of that element in the tensor product of matrix algebras. Okay, now we want to consider the Lie algebra GLN. It's well-known Lie algebra with standard basis EAB with well-known commutation relations. And what we want to do from this, for any complex number C, let's consider the matrix E minus C. So what basically you put Eij minus delta j in the ijth place, but we want to consider this as an element of this algebra, of tensor product of matrix algebra, of algebra of n by n matrices, and universal enveloping algebra for GLN. So that's the element which is explicitly written here. So the smalls E are usual matrix units. So we need to distinguish between these matrix units and elements of U of GLN because multiplication is different. So E capital are elements of U of GLN. Okay, now if you take tensor product of several such objects, that we consider this as an element of this algebra. How you do this? Well, that's quite obvious interpretation here. If you take E minus C1, you think that this matrix lives in the tensor product of the first copy and U of GLN. Second factor lives in the second copy and GLN. So all other components in other matrix algebras just identities. This is how you interpret. So altogether, this is an element of this algebra. And here is the definition of the quantum immanent S lambda. By definition, this is that expression. You take 1 over h lambda, where h lambda is just the product of all hooks of lambda. And you take this tensor product of those elements, multiply by that phi u. So if you come back for a second here, so this tensor product lives here, and remember phi u actually lives in this product here. Therefore, you can multiply them. You have an element of this algebra, and you take trace with respect to all matrix factors. So this gives you an element of U of GLN. So this is how you define it. And this is called S lambda. And certainly what I didn't explain, that CR here, now not arbitrary numbers, but actually the contents of the corresponding boxes. So we have numbers from 1 to k occupying those boxes. And so CR equals the content of the box occupied by R in that particular tableau. And the other thing, I did mention that, in fact, on the left-hand side, there is no U. It's S lambda, and this is a part of the theorem. We need to check this actually well-defined. So I wrote this using a particular standard tableau, but in fact doesn't depend on the tableau. So whatever standard tableau you choose, you have the same element of the universal enveloping algebra. So therefore, this is a well-defined element. Okay, and in this particular example, if you take just one column diagram, you will get quantum minus, and they can be explicitly written as this. It's also called as known as Capelli elements, or you can get quantum permanence. When you take one row diagram, you have elements like that. So in fact, these ones were introduced by Nazarov earlier than for that particular case. Okay, so, and what are they good for? In fact, all of them belong to the center of the universal enveloping algebra. They are Casimir elements, if you like. So all of them are central. That's first thing. Moreover, if lambda runs all diagrams with at most n rows, you have linear basis in the center. So every element of the center is a linear combination, unique linear combination of those elements, of those quantum immanents. So if so, then as before, using the same ideas we used many times in this talks already, you take product of two such elements, you have a unique linear combination of other quantum immanents. And we can use this theorem to show actually that those coefficients are precisely the specializations of our Littlewood-Richardson polynomial if you put all ai's to be equal to minus I. So you've got exactly those numbers here. So, and if you, actually this is the formula here, if you make this substitution explicitly, here is explicit formula. So what's remarkable here is that those numbers are non-negative because of the positivity property of Graham. So all those differences are positive if they occur in that expression. Okay, so these are a couple of numerical examples, show how they look like. For n equals if n greater or equal than 3, we have this. So in fact, those coefficients are independent of n if n is big enough. If n is small, you just remove those summands which have more than number of rows bigger than n. And the second application is to the equivariant cohomology of the Grassmannian. So this time we consider action of the torus on the Grassmannian, and then the equivariant cohomology ring is a module over the ring of polynomials in n variables, which you interpret as the equivariant cohomologies of a point. So then this ring has a basis of the equivariant Schubert classes, which labeled by the same set of diagrams as in the classical case. However, the multiplication rule, now those coefficients here, they now depend on those t's. So, and here is the second corollary, that again, those coefficients here are specializations of the Littlewood-Richardson polynomials, but you need to take this substitution. So all those parameters a have to be taken to 0, except for a few, starting from minus n plus 1 up to n, you just given negative t's here. Okay, and so in particular, you can see that these are polynomials in the differences. That's exactly the form in which Graham proved his positivity property. They are polynomials ti minus tj with I greater than j, because we changed sign here. Okay, so, and the important remark is this. So if you think of these coefficients d lambda mu nu, and think of them as polynomials in the AI without substitution, they do not depend on n and m, because because this the Littlewood-Richardson polynomials only depends on lambda mu nu. There is no dependence on the variables here. So this gives you the property for this structure coefficients in the equivariant ring, equivariant cohomology ring. So, and this is, I call the stability property. So as just this is a remark that the Basel rule of Knudsen-Tau was manifestly positive. And actually this is our rule with Kramer actually gives a manifestly stable formula for those coefficients. And if here is an example to illustrate what happens if you increase n and m in terms of these variables which occur in the Grassmannian. So in fact, if n and m big enough, say n greater than 3, m is greater than 4, then the rule for this product looks like this. You can see that all these coefficients which occur here, they do not depend on n at all. They are independent of n. But they do depend on m in a very controlled way. So if you increase m, that you just need to increase all indices by 1. So in fact, that stability property was then explained by Fulton by using I mean, he explained geometric meaning of that. So what happens if you take n-dimensional subspaces in m-dimensional space, or you take n-dimensional spaces is n plus 1 dimensional space? What is connection between the structure coefficients? It turns out this is the same. So it looks striking at the first sight, but actually he explained this as certain rather simple property of the Grassmannians. Okay, that's where I would stop. Thank you very much.